In today's section, we will be designing doubly reinforced cantilever beam. So I will show step-by-step procedure of designing of doubly reinforced cantilever beam. So this is the problem. A cantilever beam of 4-meter effective span carries a service live load of 40 kN per meter. The width of the beam is 230 mm. Design the beam for flexor and shear. Sketch the details of reinforcement. Use M20 and Fe415 steel. So what they have given? So they have given cantilever beam of 4-meter effective span. So our L is equal to 4 meter and that carries a service live load of 40 kN per meter. So live load is equal to 40 kN per meter and width of the beam is 230 mm. So B is they have given 230 mm. And what they have said to design the beam for flexor and shear and by using M20 concrete and Fe415 steel. So our FCK is 20 Newton per mm square and Fy is 415 Newton per mm square. So this is the data we have in this problem. So to start the problem, so effective depth is necessary for all the calculation. We'll go for the calculation of effective depth. So step 1 is to find out the effective depth. For that, as per clause 23.2.1a, page number 37, what it says we'll see. So this is the page number 37, clause 23.2.1. The vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratios are not greater than the values obtained as below. So basic values of span to effective depth ratios for spans up to 10 meter. So for cantilever beam they are given 7. So now we are designing the cantilever beam. So we'll go with this. So what they have mentioned here, they have mentioned our L by D ratio for cantilever beam should not be greater than 7. So I have taken our L by D ratio as 7. So now we are calculating effective depth. So I shifted D to here and the L divided by 7. So L we have got is 4 meter is nothing but 4000 mm. This is capital L. They have given effective span. So capital L divided by D. So our effective span they have given is 4 meter. 4 meter is nothing but 4000 mm divided by 7. So substitute all the value. After simplifying we'll get D as 571.42 mm. So I'm making it approximate value, that is 575 mm. This is our effective depth. So after the calculation of this, so we'll go for the overall depth calculation. For that we need to assume the effective cover. So I'm taking it as 50 mm. So now we can calculate the overall depth. Overall depth is nothing but it is denoted as capital D. So our effective depth plus effective cover, substitute all the value. After simplifying we'll get our D as 625 mm. So this is how we calculate the overall depth. So after this we'll go for the calculation of ultimate load. So next step is to calculate to find out the factored load. We'll see. So now we'll go for the self weight of beam. We have the formula for that. The formula B into D into rho. Rho is density of the RCC, that is constant 25 kN per meter cube. Substitute all the value. So substitute all the value. After simplifying we'll get 3.59 kilonewton per meter as our dead load, self weight of the beam. So the given live load is 40 kN per meter. So now To get the total load, we need to add the our given load plus our self weight of the beam, that is nothing but dead load plus live load. So our dead load is 3.59. So our given load is 40. So substitute all the value. After simplifying, we'll get our total load as 43.59 kilonewton per meter. This is our total load. So now we'll go for the calculation of ultimate load. It is also called as ultimate load. So it is denoted as WU. For this we have the formula 1.5 into W. W is nothing but our total load which we have calculated. So substitute all the value. After simplifying, we'll get our ultimate load is equal to 65.38 kilonewton per meter. So this is the process for calculation of the ultimate load. So after this, we'll go for the calculation of bending moment. So step 3 is to find out the bending moment. For cantilever beam, we have the formula for bending moment. Mu is equal to WL square divided by 2. So substitute all the value. So our W value which we have got is 65.38 into our effective span value is already given in our problem, that is 4 meter divided by 2. So after simplifying, we'll get our Mu as 523.04 kilonewton meter. So in terms of Newton mm, that is 523.04 into 10 to the power of 6 Newton mm. So after the calculation of Mu, so next step is to calculate the Mu limit. Next step is to find out the Mu limit. For that we have the formula. Mu limit is equal to 0.138 FCK BD square. So substitute all the value. 0.138 our FCK given is 20. So our B value is 230 and D is 575. So after simplifying, we'll get our Mu limit value as 209.88 kilonewton meter. So in terms of Newton mm, 209.88 into 10 to the power of 6 Newton mm. So this is how we calculate the Mu limit and Mu. So from these two, it clearly says our Mu limit value is less than our Mu value. So when our Mu limit is less than Mu, so our Mu is greater than Mu limit. It means it clearly says that our section is over reinforced. So our given beam is W reinforced beam. So we need to design the beam as doubly reinforced beam. So the beam is designed as doubly reinforced beam. So by calculating the Mu and Mu limit, we'll come to know, so our given beam is singly reinforced beam or doubly reinforced beam. By calculating these two, we'll come to know. So this is how we'll find out our given beam is singly reinforced or doubly reinforced. This is the procedure. So since our given beam is doubly reinforced beam, so we need to find out the area of compression reinforcement as well as area of tension reinforcement. So in our singly reinforced beam, we only calculate the area of tension reinforcement. But in case of doubly reinforced beam, we will calculate the both area of compression as well as tension reinforcement. So next step is to calculate the area of compression reinforcement and tension reinforcement. We will see. So step 4 is to calculation of the area of compression reinforcement, that is denoted as ASC. So for this, we'll refer as per G1.2 page number 96 what it says. So this is the page number 96 of your code book IS 456. 2000. So G 1.2 section with compression reinforcement where the ultimate moment of resistance of section exceeds the limiting value mu limit, compression reinforcement may be obtained from the following equation. So by using this formula we'll calculate the compression reinforcement. So we'll see what they have mentioned here. When our mu value is greater than the mu limit value, we need to calculate the area of compression reinforcement by using this formula. So they are mentioned. We'll see now. So I have written the same formula which is given on page number 96. That is mu minus mu limit is equal to FAC into AC D minus D dash. So now we need to calculate the AC. So I have rearranged it. So AC is equal to mu minus mu limit divided by FAC into D minus D dash. So call it as equation number 1. So to find out the AC, so we have the value of mu and mu limit and D as well as D dash. So what is unknown here? Here FAC is unknown. So now we need to calculate the FAC value to find out the AC. So we'll see. So for find out the FAC value, we need to refer the SP16. So now we need to find out FAC value by using SP16 and page number 13 of table number F. So for that, so to find out the FAC value, now we need to calculate the D dash by D value. So D dash which we have assumed was 50 mm. So 50 divided by our D is 575. After simplifying, we'll get our D dash by D value as 0.08. So by using this value, we'll calculate by using this value and with the help of table number F, we'll calculate the FAC value. So we'll see now. So this is the page number 13 of SP16. So our D dash by D value which we have got is 0.08. So 0.08 is not there, but it is there in between 0.05 and 0.10. It comes in between these two. So by using this value, so our value which comes in between these two. For 0.05, the corresponding Fy value is for 4 and 5 is 355. And for 0.10, the corresponding value is 353. So by using this value and we'll calculate the FAC value by doing interpolation. So I will show how to do the interpolation by using this value. I will show. So I have written the same values which is given and page number 13 of SP16. So for 0.05 we have the Fy value 355. So now we need to calculate the 0.08. What is the our FS value for 0.08? So for 0.10 we have the value Fy value 353. So now we'll calculate the FSC value for 0.08. So by doing interpolation, sir, FSC is equal to, we'll take the greater value, that is 355. 355 minus, I'm taking minus because this value is goes on decreasing, so I'm taking minus bracket the greater value minus least value, that is 355 minus 353 divided by the greater value minus least value, that is 0.10 minus 0.05 into the value which we want to find out, that is 0.08. 0.08 minus the least value, this is 0.05. So substitute all the value. After simplifying, we'll get our FS value as 353.8 Newton per mm square. So our this value is lies in between these two. It comes in between these two. It means our FS value is right. So now substitute the FS value in our equation number 1 to get the AC value. So now put the FAC value in equation number 1. So our AC is equal to, substitute all the value. After simplifying, we'll get AC value as 1685.96 mm square as AC value. So after this, the next step is to find out the number of bars and area of each bar. For that, we need to assume the bars. So now assume 25 mm pi bars. You are free to assume any diameter of bars. I am taking 25 mm. So after that, we'll go for the area of each bar, that is small AC is equal to pi by 4 into diameter 25 square. After simplifying, we'll get our AC value as 490.87 mm square. So after that, we'll calculation the number of bars required to carry this AC. So number of bars, that is capital AC, which we have got area of compression reinforcement, that value we need to substitute. After this, area of one bar, that is just we have got is 490.87. So after simplifying, we'll get the number of bars is 3.43. So we cannot provide 3.43, so I am taking it as 4 numbers. So our now AC provided is equal to number of bars into area of one bar. So we have got 4 numbers. So 4 into area of one bar is 490.87. So substitute all the value. After simplifying, we will get our AC value as 1963.48 mm square as AC provided. So this is how we calculate the AC provided. So after this, so provide 4 numbers of 25 mm pi bars at compression reinforcement. So where it comes, now we are designing the cantilever beam. So in cantilever beam, it comes bottom side. So next step is to find out the area of tensile reinforcement, that is denoted as AST. So now refer G1 to page number 96. What it says, we'll see. So this is a page number 96. The total area of tension reinforcement shall be obtained from the following equation. So they are saying the total area of tension reinforcement will get by using this formula. AST is equal to AST1 plus AST2. So our AST is nothing but area of total tensile reinforcement. AST1 is area of the tensile reinforcement for a singly reinforced section. For MU limit. And our AST2 is ASC into FAC divided by 0.87 Fy. By using this formula, we'll calculate the AST2. So we'll go for calculation. So for AST1, I'm taking, they have said to use the tensile reinforcement for a singly reinforced section to calculate the AST1. So that is, I'm using this formula XU divided by D is equal to 0.87 Fy AST divided by 0.36 FCK B into D. So both side denominator D is there. So I will cancel D, and after cancelling, our AST is equal to 0.36 FCK B into XU divided by 0.87 Fy. So I will show this. By using this formula, I will calculate the AST1. So I have written the same formula which is given on page number 96. That is AST is equal to AST1 plus AST2. For AST2, they have given the formula. And for AST1, so I am using which I have just shown in codebook. From G1.1a, XU limit divided by D is equal to 0.87 Fy AC divided by 0.36 FCK B into D. So in denominator, both side D is there, so it will get cancelled. After that, rearrange it So AST is equal to, it goes here and it comes down. So 0.36 FCKB into XU limit divided by 0.87 Fy. So by using this formula we will calculate the AST. So our XU limit is equal to XU maxima. So which is given on page number 70. So XU limit divided by D is equal to 0.48. So in this formula we need to calculate the XU limit value. So our XU limit is equal to 0.48 D. Our D is 575. So substitute all the value. After simplifying we will get our XU limit value as 276 mm. So this formula is given on page number 70. Page number 70 of IS 456 2000. You can see there. So now we have got XU limit value and all the value. So substitute all the value. 0.36, our FCK is 20 and B is 230 and XU limit value which we have got is 276 and 0.8 our FY given is 415. So after simplifying we will get our AST1 value as 1265.90 mm square as AST1 value. So now for AST2 I have already shown. This formula is given on page number 96. So by using this formula we will calculate the AST2. So our AC value is 1685.96 into FSC value is 353.8 and 0.87 into FI value is 4 and 5. Substitute all the value. After simplifying we will get our AST2 value as 1653.10 mm square. So now we got the AST2 value one as well as AST1 value. So substitute these two value in our equation number 1, that is this. So substitute AST1 and AST2 value in equation number 1 to find out the total tension reinforcement. So substitute all the value. After simplifying we will get our AST value as 2918 mm square. This is our AST value. So now we need to find the number of bars. For that again we need to assume the diameter. So I am taking 25 mm pi bars. The area of 1 bar is equal to small h is equal to pi by 4 into 25 square. We will get 490.87 mm square. So after this we will go for the calculation number of bars. So AST divided by area of 1 bar. So our AST is, which we have got just now, that is 2918 divided by AST value is this one, 490.87. After simplifying we will get number of bars is 5.94. We cannot provide 5.94 bars, so I am taking it as 6 numbers. So now we will calculate the AST provided. For that we have the formula number of bars into area of each bar. So 6 into 490.87. So after simplifying we will get our AST provided as 2945.22 mm square. This is our AST provided. So now provide 6 numbers of 25 mm pi bars at tension reinforcement. So now we are designing a cantilever beam. So it comes on the bottom side. So this is how we calculate the area of tensile reinforcement.